this a to b little f of x and dx is calculated just like this. So using that notation. Is this notation okay? You got used to this notation by now, right? You plug in a and b and subtract it off. Good? All right. Any question about the notation? You plug in fb and fa and subtract off. That's the notation in here. So in particular, it doesn't say in how to find the antiderivative. If you have found an antiderivative, this is the next step. And also, and there is this important question. I'm going to call this the big question of the semester. That number one is that can we always compute antiderivative and you're going to learn more technique in the Calc 2, and there's a book of this integral tables, and there's Wolfram Alpha, and there's Mathematica, and they have everything built in. You just plug in and hit enter. It tells you we don't have an answer, or we do have an answer, but you will find some example if you randomly try that these can't find an answer. So their example, you can't find it. Next question is a computability question, right? Computability question. So maybe there is an antiderivative we can't compute it. Maybe there is a number in the real line, number line, that we don't have a notation. But you clearly understand there is some position right there, right? You know, if you look at the graph of y equals x cubed plus x to the fifth plus x plus 1, it crosses x-axis right there, but we do not have a notation to describe it. Things like that. Is it possible there's out there a way to describe a function just like we did with the net area function? In some words, we can describe this function, but there's no way to calculate it. So that's the next question, is does it exist? Does it exist in non-elementary form? Does that make sense? It's not e to the x and sine x, none of those. But in words, it might be described and a function exists. So this, does the function exist, make sense when you understand a function in the sense I introduced in the beginning of the semester, just like the net area function. All right, so what about this function in here? So for example, f of x sine 3x minus cosine 5x divided by 1 plus x squared. Who remembers this function? Everybody remembers this function, right? That's something, homework problem, is that right? And you sketch the graph of the function. The question is that what is an antiderivative of this function? It is not elementary. The question is that does it exist? Okay? And so let me show you the, I thought I pulled it up. The answer that I have in here, you will have this code. So this is a graph of that function, sine 3x minus cosine 5x divided by 1 plus x squared. All right? And then next thing we consider is I give you a new base, 0. I hope you change that base 0 to 0 when you do the code. I change the base to 0. So I looked at area from 0 to whatever, if for example f of 2, and there is a net area. So I plotted that area function like this. So that's the relation. Given this function f of x, I created a new function. It's called net area function. So let me ask you this question. After you go through this SAGE problem, you do understand the algorithm of net area function. Is that right? You fix. Still have a question about not understanding what this net area function is? Any question? Specific question? Right? Okay. Is the net area the function to you? Abstract way of function, not given by formula. Any question? It's very important. If you don't understand this net area function as a function, and whatever we do today is just manipulation and mean nothing to you. Any question? You want me to go over a little bit? Explain one more time? Could it be the same thing? So let's go and sketch this one. I gave you that photo thing then in the discussion area. It's going to be the same thing, but let's go over one more time. So I'm going to sketch that. over here, that's the graph of this function that I wrote down in here. I'm going through that algorithm one more time. What is this A? It's a net area function, right? A is the name of the function, and AX is supposed to be a number, correct? So given input X, you have to understand, you go through some sort of procedure, and you get an output number, correct? So this algorithm is the following. There's some fixed number I gave you, the 0, and this is the part of the setup, and X is there. It could be to the right of 0, to the left of 0, it doesn't matter. I give you an X, and you think about these two numbers, 0 and X. This is the algorithm, okay, 0 and X. 0 is here, maybe X is over here, random. It looks like 1.5 somewhere. This is my random X I located. Next thing is that you consider this net area. Here's a little bit of negative area down there. Here's a little bit of a positive area there. There's a little bit of a negative area there, right? And then you calculate the net area over this interval I gave you, 0 to 6. 0 to X, I'm sorry. And we don't know what that area is. You can certainly think about that there's this number, right? Positive or negative doesn't matter. There's this number. So net area, I call that L. We can't really compute. You have to use a computer to approximate this value. But you know the existence of this number, right? And then, okay, X was the input, and 0 is a part of the setup. You never change. And then I got this number L. Input and output. And then there is a function. Whenever you have input and output, and you can sketch that in the horizontal axis, input, vertical axis, output, and visualize this input-output relationship, not through the table, but from the graph. And there it is, the graph. If I go to 1.5 about there, it's telling you the area, the net area was roughly 0.35 and things like that.
That's kind of like an acceleration when we did graph acceleration of velocity as derivative.
In a way that you were changing that quantity to exactly right. Idea of the right. There's a quantity that is a little bit abstract, like velocity, slope of the tangent line, or rate of change of the velocity, which is acceleration. This quantity is a little bit abstract. It is not like a position of the particle. Then we turn this one into a position, just like a speedometer. So go through that process in your mind. So there's some gadget that allows you to visualize the quantity in a vertical dot. And then here it is. And if you change that x values, the net area is represented as a vertical point in here. So we visualize how is net area is changing as you change the right limit in here. Sometimes this net area is increasing and sometimes decreasing, right? Because sometimes you pick up the negative region as you go to the right and fixing the left-hand limit. Go to the further to the right. Sometimes pick up negative region and sometimes pick up positive region. So as you do that, area increases and area decreases. So these numbers turn into a vertical height in here and showing you that as we go to the right, and how is this net area changes. Not only is it just a behavior, the key thing is that you recognize this input and output relations as an abstractly defined function. You understood the algorithm, there's no formula. All right. And another part of the homework problem was I did a lot of sketching the secant line, but you only asked to do the secant line just at around 2. So what is the slope of the secant line at 2 with the interval 0.01 was this formula, right? How much the y-coordinate changes, a of 2 plus h, that's the net area value. How much, would be the average rate of change of the net area, right? Average rate of change of net area. This is net area up to 2 plus h, net area up to 2 divided by how much input changed. Okay, so things like that. So I sketched the the slope of the secant line there. It looks almost like a tangent line there, of course. That's how we define the tangent line, when secant line where this one is approaching 0. So I sketched lots of other secant line using this formula. Looks a lot like a tangent line there. Okay? And also I asked you to compute the value of this one with f2, and then it's supposed to be very similar to that. Okay? All right. Now that was just discussion on the meaning of this A, and what is A? It's the net area function. On purpose, I went through and introduced the net area function in this way, is more algorithmic way, so that you don't think about the formula too much. But see if that following makes sense. Isn't that just the following, that AX, the net area function, is given by A to X, ft dt? You just change that integral variable to t. So let's think about what this one really means. A is a net area function, and then there was a procedure of thinking about the value of AX, but this is just a net area from A to X, so we have this definite integral notation. So it looks like a formula, but to actually compute that, you need an antiderivative of f of t for that evaluation theorem, and sometimes you don't. So this is the best notation we get to represent the net area function. Make sense? Okay. Although I introduce this in an algorithmic way, there is this very concise way of describing the algorithm right there. AX is integral A to X, ft dt. Make sense? Right. This is a number for x given. If x is not given, then A is just representing name of a function. Whenever x is given, this is how you calculate it, right? You can use Sage to get an approximate number of this one. And in this last Sage problem, I ask you to actually compute the rate of change of this one. For example, if you have AC, it was actually 2 divided by plus AC divided by H. We can use Sage to calculate individual points. We don't have a closed formula, so we can't take H approaches 0, but we can calculate something like this. This is supposed to be very close to the value A prime of C, don't you think? Right? If H is approaching 0, it becomes this number. That's the definition of a derivative. So I define the function in an abstract way. Now I'm thinking about its derivative, right? And then I ask you to compute this function value at C, which was 2, just for that one point, C equals 2. These two were actually very close. First 3 digits or 4 digits were the same number. So this is a Sage experimentation to see that this abstractly defined function that we understand and its derivative looks like f of x. Okay? So I'm stating that fundamental theorem of calculus part 1. Sounds like important theorem. It goes like this. Let f be continuous on some interval, closed interval, a to b, capital A to b. And A is in interior of this interval. Shows that. Then the net area function capital A, we denote it like this, is differentiable on any point in that interior of the point. Okay? What we did in that homework, and very little bit at the last minute of yesterday's class, I introduced the notion of this function, how it's algorithm of this function. Now I'm talking about whether it's differentiable, the derivative exists, right? So the theorem says it's differentiable. And if it is differentiable, you also want to, then what is the derivative, right? So I'm writing it down here. The derivative of that abstractly defined function is that little f of x. and period. I'd like to state Fundamental Theorem of Calculus Part 1 in this form, and I'll also give you a slightly different notation that book might use. But this is the important part. So AX is described in words like that, is a function. Not only is a function, it's a differentiable function, and its derivative is the one that we started with, f of x. So let me go back to that big question. The question is here. Fundamental Theorem of Calculus Part 2 says, if you found an antiderivative, there's a wonderful way of calculating the area. But question is that if the function is crazy as this one, does an antiderivative exist? We can't calculate it, but can we assert the existence of this function? Can we describe that function? What's the answer? Why is that a yes? I think that's a perfect answer. Just the net area function we described in this theorem asserts that the derivative of a is f of x. So capital A is an antiderivative, correct, of little f of x. So what is that function? We can't describe it in closed form, but we can describe it in words. There's this function and algorithm whose derivative is little f of x. That answers the existence of antiderivative. If you think about ask that philosophical question, what do you mean by existence? It's not existing in formula form and existing in the form of idea. And that idea is actually very rigorous in here. Okay? Make sense? So you actually use Fundamental Theorem of Calculus Part 2. You will never think about this Fundamental Theorem of Part 1 unless you're a math major. Part 1. You will always deal with the Part 2, right? But what does the Part 1 answer again? To summarize it, if somebody asks, why is there a Part 1? What is the role in this indefinite integral? What is a good answer for the role of this Part 1 in mathematics? Not finding it. Existence, right? Existence of antiderivative. You can't really find it, but existence of antiderivative is explained. It always exists. Okay? Almost it. So, but there are a couple of problems they throw in. Just make sure you understand this theorem correctly. So that's exercise problem we're going to do. So here's a little notation. Something you already know. If I write down x squared, it looks like a polynomial, right? Polynomial is not a function. Polynomial is just a formal object in mathematics. But you can use that polynomial to a function, right? But you don't want to sometimes name all the function f and g. So when I write x squared, you immediately understand x squared is a function, right? Right? Not polynomial, it's a polynomial function. So d dx makes sense, and then you immediately write 2x, right? I did not name any function in here. There's no f or g, but you understand this notation. Okay? How about this one? a2x, ft dt. Does it look like a function or a number? Someone actually brought up a very good point. Is this a number or function? And I said this is a number, right? And x squared, is this a function or number? If x is a number, x squared is a number, right? If x is not a number and x squared is not a number, it's a function. You're already thinking about this one, but this whole thing is a definite integral, right? If you go a to x, that's the area, net area. Net area is a number.
Okay.
So this looks like a number, right? Right, ft is a function. But if I write down 0 to 1 on ft dt, is this a function?
So overall it's a number.
Overall it's a number, that's right.
Okay.
Ft is a function, but the whole thing is a number. The whole thing is a number. But can we look at it as a function? Just like x squared.
If you just look at the interior.
No, the whole thing. Can we look at the whole thing as a function? That's the challenge here. What about that ax? Wasn't that ax looks just like that? Can we look at this entire thing as a net area function? As you vary x, not ft. As you vary x, it gives you different number. Fix a, fix ft. No, the function doesn't change. But if I change that upper limit, and you can view this as a function, right? What is that function called? Net area function. But I didn't name it ax here. This whole notation is kind of representing the net area function. Does that make sense? Therefore, we can put this ddx notation. Just like x squared. I didn't name that function, but you understood what I mean by that. And is that right? No, not ddx. This let me. Without this, can be viewed as a net area function.
Okay.
So it's a function. We can put ddx in front of it, right? You don't usually put ddx in front of a number, and you have to interpret that number as a constant function, so that ddx makes sense, right? All right. So, any more question about this notation? I don't know how to say this one. Is that the term is on the fly, kind of? You don't have to name everything on that on site. You just do this operational term. So if you recognize this entire thing, the bracketed thing, as a function, then ddx makes sense. And what is the answer? F of x. No, not t. T is only for the. This whole thing is ax, right? What is the derivative of ax? Is little f of x. T disappears. And how do you explain this thing? What theorem allows you to conclude this is f of x? Not the lemma. What's that? Part 2. That's what is stated right here. Fundamental theorem of calculus part 1. Sorry about part 2. Part 1, but it's introduced later. That confused me, the order. Part 1 says this is true, right? This is a very concise version of what? FTC part 1. Is that right? This whole thing is a correct version. It gives you explain all the context correctly in here, but often we're busy. We just stick to this type of abbreviation. Make sense? All right. This is a circular reasoning, but let me interpret this one another point of view. All right, ddx of a2x ft dt. I'm going back to the fundamental theorem of calculus part 2 and calculate inside there. I'm not touching ddx. I'm leaving that ddx in there. So I want to calculate that this integral as a definite integral, treating a and x as a number. So what does that say? Fundamental theorem of calculus part 2 I'm about to apply inside of this ddx part in here. What's the first sentence in the fundamental theorem of calculus? We found an antiderivative. Can you find an antiderivative of ft? In the aid of part 1. Capital FT. But there's a better than capital FT. This is capital FT looks like some random antiderivative we don't know. But there's a better than capital FT by looking at this part 1. You can use AT. Fundamental theorem of calculus part 1 says there is something called AT, net area function. That is an antiderivative. That's what the part 1 says, right? So rather than using FT, you can use AT. All right? Does that make sense? So it's AT. Isn't that what the theorem says? Fundamental theorem calculus, right? What is the first input in here? X. Second input? A. Part 2. Correct? Not capital. We can use A. We can do a little bit better. That's what I'm saying. That's right. Right. So this is the same as AT, not FT, bracket AX. Is that what you want? Okay, good. So the same thing. But it is expanded this way. So is this changing? Is this a constant function AA? Am I right? A never changes. But this is a function. X is changing. X is actually a function in there. So some rule says it's ddx of AX and plus 0. Is that right? Minus 0, actually. Then what do you know about this ddx AX? It's f of x. So we cover that. Kind of conjunction with the part 2, like manipulating and putting it together. But this is not a proof, right? That antiderivative of ft being is actually the part 1. But I mixed them together to make sense out of this notation. Okay?